What's going on, guys? It's the Unhinged Engineer here, and today I want to give a little bit of an introduction to deep learning techniques for computer vision. So if you're like me and you didn't study this stuff in college, but you see it kind of creeping into your industry, whether your industry is aerospace and defense like mine, or manufacturing, or biomedical sciences, computer vision is slowly starting to creep into our work. Either A, it's that, or B, you're genuinely trying to break into this industry and take some initiative. It can be really hard sometimes to kind of see through the fog of war when you're learning about all these different topics at once. And so I wanted to make a video that I would have appreciated when I first started, that just kind of gets pseudo technical about each of these topics, but serves the main purpose of like being a roadmap as you start to self-study these things. Three kind of caveats here. First of all, like I mentioned, I'm only going to talk about deep learning today for computer vision, but there's lots of computer vision techniques that aren't deep learning based, which I think are super cool and worth learning about, but we're going to leave those out of this video for one. Number two, I'm going to assume pre-trained models here, because if you're like me and you're just kind of given like a task like, hey, we're trying to put computer vision on this thing, more than likely than not, you're using pre-trained models, and the skill set between training models from scratch and using one that's already made are pretty different. And again, that's something to talk about in a separate video, but to prevent scope creep, I'm just going to assume everything's pre-trained and take the models as they are. And number three, I'm obviously going to assume, a little bit of like linear algebra. It's going to be primarily linear algebra for this video, but also like some calculus, math, computer science, basic stuff like that. The first three topics I want to talk about here are kind of general computer vision. And then the five after that are actually mostly layer types for these models, so that if you're trying to work with them and maybe your dimensions aren't matching, or you're not using a proper layer for what you're trying to do, like you can understand the anatomy of these models as you start to work with them. So this might be a longer one of my videos, so without further ado, let's just get right into it. That does the intro. Let's talk about images, right? So you've probably heard of RGB values before. It's pretty simple. You have a red channel, a green channel, and a blue channel. And those usually range from 0 to 255. RGB is how we store the color information for each pixel. And if you didn't know, an image is comprised of pixels, and each of these pixels, these little squares, has a color value, and that color value is encoded with RGB, right? Cool. Probably knew that already. Now, this is a little bit more specific to computer vision, right? So we have these pixels and RGB values for each. But how do we run out of mount space here? Let me just throw that on the floor. How do we store like the numbers in these image files as tensors that we send to something like TensorFlow or PyTorch or some of these other frameworks that you've heard of? Well, we usually store them in a format like this, or sometimes you send channels to the end. It's called channels last. This is channels first. I know channels technically second, but we usually ignore batch because that's variable. So this is channels first, and then this would be channels last because channels are at the end. So what do I mean by B, C, H, and W? Well, H and W are pretty self-explanatory. Height and width, simple enough. Channels are actually what we just talked about with RGB, at least at the input layer, right? So usually for an image, you've got those three channels, red, green, and blue. And so at the start of the first layer to your model, channels is more likely than not going to equal 3. It might equal 4 if you have like an alpha value or something. That's for transparency. But that's what we mean by channels, right? So it's helpful to think about, you've got an image, and it's tempting to think of it as like a piece of paper, like a two-dimensional surface, but it's a little bit better to think of it like a stack of papers, right? And here there's three individual pieces of paper, one for red, one for green, and one for blue. Now, as you get into your model, the number of channels in this currently three-dimensional tensor can change, right? So like you might have, the input to another layer have 5 channels or 100 channels, right? We draw 5 channels, 1, 2, 3, 4, 5. And each of these would have a different height and width, right? So the dimensions of these tensors are going to change as we send them through the model. And last but not least, what do I mean by batch? Well, I mainly mean how many full images are we sending through the model at once. So let's say like this is the input to your layer, your first layer. This is your image. if you're sending 2 images in at a time, there's going to be 2 of these, right? If you send 50 in, there's going to be 50. And that's kind of why this batch size can vary, because it might vary whether you're training a model or running inference or want to test your throughput on different set amounts of images, right? So yeah, batch channels, height, and width is usually how we think about these tensors when we're sending them through our models. Cool. Okay, so that's images. Let's talk about objectives, right? So there's 2 main ones here. Object detection and image classification. Now there's other ones like image segmentation that are pretty dope, but right now I'm just going to talk about these 2. Let's start with image classification because it's actually simple, or the simpler one, right? You got an image, there's a person in the, there's a thing in the image, you want to know what's in the image. Here, this would be, let me draw it in blue to show we're doing something. This is a person. You've classified this image. If there was a house in this image, then you write house, right? And usually there's one class in these images, right? Now, there's, like I mentioned earlier, there's other types of things where maybe you want to describe what's in the image, and that would be like image to text conversion, right? But right now I'm just talking about the basic image classification that if you're just getting started in ML, this is probably what you're going to see. Because one of the first problems that was actually solved with ML was for male, and they trained a neural network model to classify between different handwritten digits, which is actually difficult, right? Like I write these little weird lines in 7s. I don't really know where that comes from, but I've just always done it that way. So it might be hard. Someone might think this is a 3, right? It might look like a 3, or I might just draw it really sloppily and it looks like a 2. Like that might look like a 2. And so we trained, not we, I was just barely born, I think, when this was done, but they trained a neural network to classify between different handwritten digits for the purposes of male, right? Object detection is usually considered the more complicated task between these 2, where basically you have more than one object in the image, and you want to know where those objects are and what they are. And so you're not only doing classification, but you're also doing bounding boxes, right? So bounding boxes are usually written out in one of 2 ways. The first way is you use these corner points. So this is x0, y0, and this is x1, y1. And with those 2, you can draw the box, right? Simple enough, and you draw it out like a tensor. Or you can write it out like this. X, Y, height, width. Or you can write it out like that, right? And again, just write it as a tensor, like so, right? And so your model has to do 2 things at once. It has to draw these bounding boxes, and it has to classify what's in them, okay? Cool, simple enough. And it's just important to know what you're trying to accomplish, because that's going to affect the data you're working with. It's going to affect how you measure accuracy, you know, whether or not you can, whether or not the system's actually doing what you want it to do. Okay, cool. Objectives out of the way. And lastly, I want to talk about pre and post processing. I'm simply going to talk, I'm going to focus more on pre-processing just because it's simpler to explain and a little less circumstantial than things like post-processing. All right, so we're talking about deep learning here. We've got our fancy model with all the layer types we'll talk about momentarily. And you've got images that you're sending into the model, and you've got information that you're getting out of it, like maybe classification, right? Anything that you have to do to the data before you send it into the model, or have to do to the output of the model before you can actually use it, before it's useful information, those are pre and post processing, okay, respectively. So yeah, relatively straightforward concept here. A good example of pre-processing is normalization, right? So maybe, for example, instead of wanting all your RGB values to be between 0 and 255, Maybe you want them all to be between 0 and 1. Whoops. And you can do that like multiple ways. Like the kind of simple way is linear scaling. And here the minimum is 0 and the maximum is 250. So that's 255. So that's pretty straightforward. Or you can do with statistical parameters, right? So you've got an average and you've got standard deviation. And that can be average within the image, it can be average within a batch, etc. So either way, these are both going to accomplish the same thing of normalizing everything to between 0 and 1. Another really simple example of pre-processing is what I talked about earlier with dimension ordering, right? So what if instead of tensors like this, for whatever reason, which believe me, there's a surprising amount of reasons this little detail could be a pain in the ass, you want it to be stored that way, right? And the way that these are accessed in memory is different too, so that'll affect the performance of your model. So if you're trying to convert between these two things before you send it into the model, that's pre-processing. Like I said earlier, post-processing has, a lot more nuance to it, at least in my experience, because it depends a lot on the model that you're working with. But just as a basic example, there's something called non-max suppression in models like YOLO or other things. Or I think FastRCNN uses a different type of non-max suppression. But anyway, imagine you've got your class here and you draw your bounding box, but you get a bunch of other like junk bounding boxes and you only want one. You want to suppress all the ones with the lowest confidence, right? So when we generate these classifications, I probably should mention this sooner. When we generate these classifications, they're going to have some sort of confidence or probability associated with them. And so if we have a bunch of these, like this one is probably going to be lower confidence than the first one I drew, right? Because it's just not drawn properly. So you suppress all the non-maximums. That's an example of post-processing. And for things like YOLO models, I'd kind of go, start playing hooky and just classify things. Like they generate lots of classifications, especially if your threshold is low. Then you really want to use that non-max suppression to distill down the results. Okay, cool. Now we're getting to the juicy stuff, layer types. So as you know, or hopefully know, models usually consist of layers, one after another. If you've seen PyTorch code, you write this out like sequentially. There could be convolutions beforehand, and then fully connected layers, and afterwards there can be a softmax, right? Like different layers in a row that you send images in, and then you get information out. And at each step, how you represent the information is going to change, right? And that's kind of what we talk about when we mean feature representations. Like maybe your convolution is learning a feature representation that does proper classification once you get to the fully connected layer, okay? Sorry, I'm getting a little in the weeds. The point I'm trying to get at is neural network models are like onions. They have layers, okay? And the first pair of layers we're going to talk about are convolutions and pooling layers. I'm actually going to talk about these two together because they both use something called a sliding window. So sliding window kind of works like this. Let's pretend our images are one-dimensional, which, if it's something like a signal would make sense. Pretend our images are one-dimensional. And we've got, this is our image, and this is our kernel, we're going to call it, okay? And what we're doing is we're taking this kernel, and we're sliding it across the image. So if you can tell right now, this is centered at x1. So this is like x0, x1, x2, x3. It's centered at the second element here. At the next stride, I'm just going to try to do botched animations with a whiteboard. At the next stride, now it's centered at x2, okay? We do some operation, which I'll get to in a second, and then we take another stride. Oh, this one would actually be done because we hit the edge. Let me add one more. Now we're going to shift it over, get rid of this, and then move the indices, x0, h0, h1, h2, okay? And now we're centered here, and at this point we hit the edge of the image and we're done, right? So for a convolution, the operation we're doing at each stride here is just a dot product, right? So we've got a three-dimensional vector here. Whoops. Three-dimensional vector here, in the three-dimensional vector here, we dot them, we get out a value, then we shift it, we dot them, and we get out another value, we shift it one more time, and we dot it, and get another value out, okay? If you notice here, this makes sense, right? 1, 2, yes. If you notice here, the output is only 3 long, and our input was 5. And for various reasons, you might want your output to be the same length as your input. And so that's going to lead us into kind of 2 subtopics with this sliding window concept called stride and padding, which are pretty important to understand. Let's talk about padding. So like I just said, we are effectively downsampling here in a weird way because, not a proper way, we'll get to the proper ways in a moment, but we're downsampling in a weird way because we have 5 input elements and we're getting out only 3 output elements. And we may want our output to be the same length as our input. So what we can do is pad zeros on the ends here, right? And now, if you look at this, instead of being centered at the second element, our kernel is going to be centered at the first time step, or stride, I should say. Right? So now we're going to get one here, then we're going to shift it to there, get one there, shift it to there, get one there, shift it to there, get one there, and then one more to here, right? 1, 2, 3, 4, 5. Perfect. And if you notice here, this output is 5 long, which matches our input. And all we had to do was add values on the beginning and end. Usually we do this symmetrically, but you can do it asymmetrically as long as you keep track of all your numbers and stuff. But this padding example, this is great because like as we get further into our model, we don't want our tensors to get smaller, smaller, smaller without us having any control over that reduction at each step, right? So you can use padding to vary how that happens. You can even use more padding to make your output even longer, right? Stride, varying your stride actually makes things shorter. Actually, you know what? Let me leave this 0 here. So if you noticed, at each stride here, I was stepping by 1 element at first, like by default. What if I step by 2? If I step by 2, at the first stride, it's centered at x0. And then at the second one, it's centered at x2. And at the third, it's centered at x4. So if you notice, by increasing the stride from 1 to 2, we've actually undone the effect of padding, right? So now we're shortening our output, right? And this is why like a convolution with a stride greater than 1 is like a type of downsampling that is more commonly done. Stride greater than 1, excuse me. So here the stride would be 2 because we're stepping by 2 elements, okay? All right, so now that we've talked about convolutions, let's talk about the other type of sliding window layer here, which is pooling, which is actually a little bit simpler. So we've got this input image. And we've got this, I'm going to draw it on top of the input image actually for pooling because that might help. And let's just do a 2 long kernel, right? The term kernel is used less in pooling layers because it's kind of like baked into the name, the operation that you're doing. So let's say we're doing max pooling, okay? And let's assume that this array, this is a giant assumption that doesn't really make any sense for images, but you'll see why in a second. Let's assume that this array is sorted. So x0 is less than x1 is less than x2 is less than x3, right? And we're trying to do a max pool. What we would do here is we would take the maximum of these 2 values, which is this guy, because of that, and we would just output it here, x1. Then we're going to shift this window like so. Sorry, my drawings are getting a little ugly. Cool. Now we're at the next stride. And here the maximum is x2. And then we're going to shift it one more time. You get the point. Here, now we're at x3. Okay? Now, if you did min pooling, it would be x0, x1, x2, because you're taking the lower one in this inequality here. And then last but not least, if you're trying to do like average pooling, what would basically happen, I guess I'll write it out. Won't take too long. You take the average. So this would be like, let me just move out the 1/2, x0 plus x1, x1 plus x2. The half being for averaging, right? So we're averaging between x0 and x1 and x1 and x2, okay? So instead of doing a dot product like earlier, you're doing like a set operation. And these are a little different than convolutions, not because, not to get into training, but like when we're doing that dot product, the thing that we're learning is the kernel here, right? Like we're learning parameters of this convolution that give us a good feature representation. Versus with pooling, you just have an operation that you want to do. And there are parameterized types of pooling that do involve like learn parameters, hence the name. But yeah, for the basic kind of like min pooling, max pooling, stuff like that, that's what we're talking about here. Next one, fully connected layers. So fully connected layers, also known as dense layers, I'm just going to write it out as dense because it's shorter, are effectively just matrix multiplications, right? So this is where a little bit of linear algebra comes in. W0, W1, Wn minus 1. Then this would be x0, x1, xn minus 1. Okay, sorry about that. Multiplication, addition. Okay, so effectively what we're doing here is we're multiplying this vector by a set of weights and then adding in biases, right? So usually, like with most CNNs, because we're talking about convolutional neural networks here for deep learn for computer vision, the convolutions that we just talked about are up front, and those are kind of learning like a good feature representation. And then in the back end, you have fully connected or dense layers that really have those trained neurons that serve the purpose of classification or drawing bounding boxes or whatever, right? So at this point, we have the vector in a form we want, and now we're doing like the bulk of the learning here. So we have learned weights that we multiply into this vector, and then learned biases that we add onto the result of that multiplication. So here, like y equals wx plus b. W is a matrix here because you get that diagonal, right? Yeah, it's pretty simple. Honestly, it's pretty self-explanatory. The hardest part was drawing it out. Cool. So that's you know what? I'm actually going to leave that here for a moment. Now we're going to talk about activation functions, which are pretty intimately linked with fully connected layers. I mean, they're important for all types of layers, but just with the formulas here, it serves a good purpose. So if you notice, like this is all multiplications and additions, right? And there's no nonlinearity here, okay? And so people much smarter than me, when we were first coming up with these neural network models, figured out that introducing nonlinearities into your system help it learn, help it generalize to more data, right? And so what they did was they changed this formula to this. Usually they use the symbol sigma. Some activation function applied to the result of this computation. So usually the result of this computation is called the activation of the layer, and then you put the nonlinearity on top of it and send this to your next layer. So L plus 1 is like the next layer, right? So what are some examples of activation functions? Well, I'll give you two really simple ones. The first one is something called the logistic curve, aka a sigmoid. It can look something like this. Well, that was a terrible drawing. Let me try that again. Yeah, slightly better. We'll go with it. There you go. That's better. So this would be like a sigmoid, where you've got this almost linear, like almost constant slope in the middle, but then it kind of tapers out at the top and the bottom. And you can shift this y-intercept accordingly. Okay, so that's like a sigmoid activation. So if you notice, right, like in the middle, there's this line. So for values close to 0, it almost looks like you're doing nothing. But then as you get towards extreme values, it kind of tapers off at something like 1, right? And so if you want to truncate your values between 0 and 1, which is really good if you have a ton of outliers, then, this is a great function, right? Because if you get 0, you're going to get, let's just say 0.5 here, if that's your y-intercept. But if you get a million, for some godforsaken reason, it's basically just going to approach 1. So you're really scrunching your outliers here, and that helps generalize. Because previously, if you got weird things, you could get one activation that just demolishes the rest, and you don't want that kind of behavior in your layers. You can also do something like this. This is called a ReLU, where basically on the negative side of the y-axis it's 0, and on the positive side of the y-axis it's just a line, usually with the slope of 1, so y equals x, right? And, again, this is nonlinear because you have this weird corner joint, but, for positive values, you're basically doing nothing. And this, again, just helps us train the model to learn more quickly and give us more accurate results and generalize to different data, right? And so there's other types of things like, for example, let me start with leaky ReLU. Leaky ReLU, where instead of being 0, it's just like a shallow, m less than 1. It's just like a shallow slope here. Or you can even have like a parameterized ReLU where the slope of this is learned. Okay, learned over time. So ReLU and Sigmoid are two good examples of activation functions that just introduce some nonlinearity into the model and then help it learn better. Which, if it learns better, then it infers better and has better accuracy. Okay, well, that was pretty much the bulk of it. I want to talk about residuals really quick because you may hear about something called ResNet, which is a famous model type. Basically, a residual connection or a skip layer or a shortcut, there's tons of different names for them. It's basically just, let's say you've got 2 layers, and let me draw 3. I'm not going to draw all the lines here. We've got 3 layers, and we box them so they're less ugly. There you go. 3 layers, and let's say by the time you get to the end here, you have what's called the vanishing gradient problem. Basically, you kind of done a ton of math by the time you get to this layer, especially if there's I drew 3 here, but there could be dozens of layers in a model. You get all the way to the back, and you're like, oh, I kind of forgot what I learned all the way up here, right? Because over time, you're taking these, you're doing average pooling, and you're downsampling, and you're training by you're multiplying by weights that have some noise to them as you're learning, right? So by the end of it, just kind of the wisdom that you got here is lost. What you can do is you can take this output and you can bring it all the way front, right? Or to the back, I should say. And this is what's called a shortcut. So let's call this is xi for input. This is x0 for the output of the first layer, x1, and let me draw one more, x2. What you can do is you can say, okay, let's make x2 be the output of this layer plus the output of a previous layer. You can also concatenate them. Both of those are used in different circumstances, right? For the most part, it's addition here. So these shortcuts take the output of a layer in the front and send them all the way to the back like you're throwing a pass in football, and add it or concatenate it to the output of a layer downstream. And that helps deal with various qualities of models that I won't get into more. But if you hear ResNet, it's basically just residual network, and it's about these types of shortcut layers. Okay, we are done. So, I didn't want to get too technical in this video, but I also wanted to talk about it in plain enough terms that someone with an engineering background could understand, right? Because for me, it's really easy to get caught up in a tailspin and just be like, what the hell is going on? I have no idea what's happening when you're learning about these model types. And so relying on the basics, like basic statistics, right? Like means and standard deviations, or basic calculus, like nonlinearities, or basic linear algebra, like the matrix multiplication I talked about earlier, or the sliding window concept. Relying on these mathematics that we have can really help us navigate this vast ecosystem that is deep learning for computer vision. I want to talk about this topic today because it's mostly what I've worked on since I graduated school, and it is not at all what I studied. And so in the, over a year that I've been out of college, I feel like I really learned a lot, and it just kind of helps with basic literacy and is allowing me to learn more and more. So the rate of learning is going up, which is pretty exciting. And so if you've been trying to break into this field of study and you're struggling to like get that engine started, and this could serve as like a roadmap for what you need to know, then I'm super happy, and I hope it's helpful to you. So yeah, so in conclusion, we talked about some basics like images, objectives of computer vision, and then pre and post processing, and then the types of layers that you'll encounter in these models and how they're used, what they're used for, and then some of the intricacies with each of them. So yeah, I hope you enjoyed this video. Thank you so much for watching. I'm the Unhinged Engineer, and I will see you in the next one. Please like, comment, and subscribe if you enjoyed this too. Thanks.